Alright, so today I'm going to be talking about the optimizer's curse. That's quite a dramatic name, but it's quite an ordinary problem, I would say, although it is very important to know about. Now, it's a problem in statistics, but many more people are going to be affected by this rather than just statisticians, and not even just people who have a technical job or work in science-based jobs, for example. Basically, anybody who's ever made a decision is going to be affected by this curse in some way. Now, the interesting thing about this curse is that it is intuitive, simple once you understand it, but I'd argue it's relatively easy to oversee it and to also run into the problems that are caused by it, of course. Now, I know I'm being quite vague at this point. I haven't even really talked about what this is, but first I want to talk a bit about what statistics does. So in general, it's all about making decisions based on imperfect information. And imperfect information meaning basing things on samples from probability distributions instead of basing them on the entire probability distribution. Because in general, in most situations anyway, in general, probability distributions are very hard to obtain and very hard to obtain accurately, especially. Now, statistics in general, of course, is quite adept at handling situations like this. If you have a proper model, if you make the right assumptions, then you're still going to be able to make the right decisions in quite a lot of different situations. So before we get into the actual problem of the optimizer's curse now, first want to talk a bit about how a very simple estimator that you have run into in the first statistics class that you have taken. And by the way, I am assuming that if you watch this video that you do have some background in statistics or basic probability theory. Either will do. I'm only assuming you are familiar with simple probability distributions and expectations. That's almost everything that you need to know to follow along with this. But having said that, most of this is going to be quite intuitive, and the proof is, I think, or at least it's supposed to be easy to follow along with. So by all means, if you're not familiar with this theory, feel free to join anyway. I think you're going to get quite something out of this. So let's first talk about a very simple case or a very simple problem in statistics, which is estimating the mean of some random variable. Like the average volume in a soda can or the average weight of a car, for example. Those are problems that I was introduced to in my undergraduate course. So basically what you're going to be talking about is stick to a single random variable at this point. You're going to be dealing with some probability distribution, and it looks a bit like a Gaussian. It doesn't have to be, of course. Let's call a random variable x, and the probability distribution is called p of x. Now let's say you're interested in estimating the mean, so the expected value of x. Now this one's rather simple, or straightforward at least, if you have taken a statistics class, which is just to use a sample average. And I'll write this down because we'll come back to this in the later portion of this video. It's the sample average estimator of the mean, which is basically just taking n samples and taking the normal average, where the xi here are just distributed according, just like x is in this case. And now this estimator has some rather nice properties, if I can make a little bit of space for myself here. First of which is that it's unbiased. Half the time you're going to be overestimating, half the time you're going to be underestimating, but you don't expect to be overestimating or underestimating most of the time, which is good, of course. But it's a lot better combined with the second property, which is that of minimum variance. Trying to estimate this parameter, the expected value of the random variable, using this estimator is going to have the least amount of variance that you can possibly get for any unbiased estimator. Now, as these two summed up together, or these two taken together I should say, an unbiased estimator, which is also a minimum variance estimator, gives you a truly optimal estimator. At least in one sense, specifically the mean squared error. And so there's other ways in which an estimator can be optimal, but this one's quite straightforward and very generally applicable, of course. And so in general you can just say this is a very good estimator, and you're not going to be able to do much better in general. That's safe to say. And now the optimizer's curse applies to situations in which this estimator is used and in which you're trying to estimate the mean, for example. Now the optimizer's curse applies to situations in which seemingly this estimator is quite useful. So let's say you're a business owner who's trying to figure out the cheapest way of producing a certain product. And let's say there's 3 ways of doing so, and you've run some experiments. Maybe you used each production method for 1 week, for 3 weeks in total for all of the experiments. And you figured out, well, what are the costs that I incurred during each week? And let me just make a quick graph of this so we can talk about this a little bit more easily. So let's say the first production alternative were relatively high. The second one was quite a bit better. And the third production choice was, or the third production method I should say, was just slightly higher. And I should say that this vertical axis represents the cost, and the absolute values of these bars doesn't really matter. It's all about what they are relative to each other, like how big they are relative to each other. And I'll just label this so we're on the same page. Now based on this, if you're the business owner, you might say, well, option 2 seems to be the best. I mean, option 3 is quite close, but option 2 is the best, and so we'll go with that one. And there's nothing really wrong with that. Maybe there might be a slightly better way of doing it, but the optimizer's curse doesn't apply to your choice of the best alternative, the best among these 3. Because the optimizer's curse applies to what happens after you finish your experiment and once you actually start running your business. Because you can imagine this estimate could be used to estimate the costs of your method. And after all, these are samples. I mean, if we're going to assume, of course, that these are samples drawn from the true distribution of the costs of these 3 methods, then this is an unbiased estimate. This is simply a sample average estimator. And so you should have a very good estimator. But now that I told you that the problems are going to start after you finish your experiments, and so imagine what happens then. Let's say a customer comes in with a big order. It doesn't even have to be a big order for the problems to kick in, but there'll be a lot more, or those problems will have a lot bigger impact. Let's say he wants to place an order that will take you 3 weeks to finish, which is quite large for your company standards. And so you tell him, well, we just finished optimizing everything, and so the bill for the order is looking quite good for you. And the cost that you're basing the bill for the order on is what you see over here. This is the estimated cost that you'll be using, and you could of course be talking about, well, this is an imperfect estimate, so you should be taking a bit of a margin of error into account, but discarding that for the moment, you're using this cost. And the problem with this is, even though this is a sample drawn from the true distribution, that's what we're assuming here, you should still expect to be underestimating the costs of the order. And that's what the optimizer's curse is all about. Now, before we get into the actual mathematical proof that shows that this is the case and that it really is a problem of underestimating the costs, systematically underestimating the costs, I should say, first I want to talk a little bit about the intuition behind it. Because the intuition is rather easier at least to understand. And the way you can look at this, if we're just going to assume a certain distribution over the cost, because in general, of course, you don't know the true distribution. Let me just draw this for the 3 different options. First cost was quite high, so let's say this is the expected value. Say it's also quite high. Say for option 2 it was quite a bit lower. For option 3 it was lower still. Alright, so that looks something like this, and the exact shape doesn't matter too much. But what you can see, if you have this perfect information in front of you, you might say, well, option 2 and option 3 are quite close in expected value, and so there really isn't a clear winner. And so we chose option 2, but really it's kind of a toss-up. Option 2 or option 3 could have been declared the winner either way. And so going a little bit further, you might say, well, option 2 got lucky. And here we're talking about choosing a production method, and in general you might be talking about decisions in sports or healthcare, and so the phrasing might be a little bit inappropriate. But let's, for the for a matter of convenience, just call it luck for now. Another way of looking at it actually is to talk about outliers, which is the entire problem of the optimizer's curse, I would say. Because even though we are assuming that these values are samples drawn from the true distributions of the costs of the free options, I should finish this off over here, of course. Because you take the minimum over all of these samples, you're biasing your final results towards an outlier, or you're more likely to pick up outliers, I should say. Now, when I say outliers, I'm not even talking about being 7 standard deviations away from the mean. You're just a little bit further away from it than you usually would be. And that's the problem of the optimizer's curse, being biased, specifically being biased towards outliers. And so, because we're going to be talking about bias, it's interesting to talk about the actual parameter that we're trying to estimate in this case. And so let's just quickly write that down. So in the problem of the large order that I brought up earlier, the parameter of interest that the shopkeeper would like to know about is of course the expected value of the chosen option, being option 2. And then the estimator that he's using being a sample from x2. This is then just a random variable. This is the notation that I'll be using here for estimators. But actually this is wrong, because like I said, you're biasing your estimator using the other samples, and so what you're actually doing is taking a minimum over all the different alternatives, over all of the samples of the different alternatives, I should say. And this is the estimator that we're going to be talking about today actually. Now, from just comparing these two estimators, you will notice that the distribution of these is probably going to be different. Not always, but in general they definitely are going to be different. And so you can be talking about the actual distribution. You can be talking about this bias with respect to a certain parameter that you might want to estimate, or just the expected value of this estimator. And you could also be talking about this variance. And now, the distribution and the variance, I'll leave that to maybe another video, but for now, at least, I want to just focus on this bias, which is already going to cause us quite enough problems, as we'll see. Now, this may very well be a parameter that you're estimating. There's a couple of other ones, because this situation applies quite generally to decision making, and so you might want to estimate a parameter of a different kind. So let's say, actually let me just first introduce a little bit of notation. Because we're going to, by the mu i's, we're going to denote the expected values of all the different options. Which is just a little bit of notation that's going to make things a lot less messy down the line. Then we're going to use b as denoting the option with the true lowest average cost. Maybe just use this one. And I'm going to use C as the option that was actually chosen based on the samples. And so C is going to be another random variable. And that distinction is going to be important to keep track of, to not make any mistakes down the road. I'll just this down. So this is C is a random variable. That's the actual choice that was made based on our samples, and B is the truly best option, which is simply a constant. And so this is one parameter that you might want to estimate, the one that the expected value of the option that you actually chose. Another parameter that you might want to estimate is the expected true value of your chosen option. And another that you might want to estimate, and this actually doesn't involve an expectation on this level, here we go, is simply the true value of the truly best option. And of course this does involve an expectation because it's here, it's in the definition of the muse. So these are 3 parameters that you can try to estimate, and I won't show it for each one of these, but what I will show, what in general does hold, is that each of these three estimators, or for each of these three parameters, this estimator is not unbiased, and your results are going to be in general biased by quite a lot. So let's look into the proof for that. Or actually, before I do that, I want to talk about the actual impact, because I won't be showing you a proof of the size of this bias, but I will show you an example of a meta-analysis that I found in a paper from which I'm taking all of this. The paper in which you first read about the optimizers curse, they were talking about a meta-analysis that was done in 2001. Basically, they studied 38 studies. I'll go back up again. And in each of those studies, they studied situations just like this. They made decisions based on imperfect information. And so what they did is they compared the estimated value of the chosen option to what would have happened if they hadn't run the analysis at all. So whatever the company was doing before the method or the option or whatever you were talking about, whatever they were talking about before it was optimized, they were comparing that to what they estimated to happen after the optimization. And this is what they call value added, or the estimated value added in this case. And so over the 38 studies that were considered in the meta-analysis, the total, I should look in my notes here, the total estimated value added was $487 million, which is quite a lot, and I should say US dollars. So 487 million estimated value added. Excuse my handwriting. And so what they did is for each of those estimates, they basically assumed that they came from a normal distribution. We'll set the mean of this normal distribution to whatever value estimate that the study authors came up with, and we're going to assume that the standard deviation of that distribution is 5% of that expected value. And they did that for all 38 studies, and what they came up with is that based on that, on those distributions, that in general the estimated value added would be $555 million. So basically what they were doing is they were trying to estimate probability distributions of value estimates out in a wild of distributions that could actually occur in real life, trying to estimate those with realistic looking values, of realistic magnitude of course as well. And they were assuming that there was like a 5% standard deviation. And what it amounted to was already a 14% overestimated value added. So I'll write this down as well, because there's going to be a few more numbers, because it's going to actually keep getting worse. Estimated value added and over estimation. So for 5% standard deviation, like I said, there was a $555 million US dollars estimated value added, which compared to the quote-unquote for true value added, that's a 14% overestimation. Now they also ran this for 10% standard deviation and 25%, and in the first case there was $678 million US dollars in estimated value added, which amounts to 39% overestimation. And the final case is going to be even worse, because there's no longer in the millions but 1.111 billion US dollars, which amounts to 128% overestimation. The meta-analysis only considered 38 studies in one company. So this isn't about an entire industry even, this is about one single company. And so just based on this information, you can see that the effects of this optimizers curse can be significantly high. And yeah, I should say the paper did go into some detail about the actual overestimation percentage for just some normal models, models using normal probability distributions. But if you're interested in that, I'll leave a link to that paper at the end of the video so you can check that out yourself. So given that we know this is a serious problem that happens consistently if you're not careful about your value estimations, and if you do that so incorrectly, the bias in your value estimate is going to be very, very significant. And we should talk about the actual proof that shows that this is a problem. And to do this, I'll scroll up just a little bit to remind us of the notation we are using. So mu I is to denote the expected values of all of our options, b is the truly best options index, and c is a random variable denoting the chosen index based on the experimental data. Now the way to prove the optimizer's curse is true, at least for I should say one of these parameters, namely this parameter, the expected value of the true value of the chosen option, which I apologize is quite a mouthful. We're going to show that this estimator with respect to this parameter is not unbiased. So the way to do this, in a relatively straightforward proof I would say, is using two inequalities. First of which is that the true value of the truly best option is always less than or equal to the true value of any other option. And so what this implies is that the true value of the best option is also less than or equal to the true value of our chosen option. Now again, this is going to be a random variable, but this inequality will hold always, regardless of what this random variable becomes. And now the second inequality that we'll be using is the one that says, well, our estimate of our chosen option is always going to be less than or equal to the estimate of any other option, which implies that the estimated value of our chosen option is also always less than or equal to the estimated value of the best option. And now we transform these inequalities slightly by subtracting the same quantity from both sides of this first inequality. I should write this a little bit more neatly. Say that's xb. This is mu c minus xb. And then we take this inequality and we flip this around. We multiply by minus 1. What we'll be left with is minus xb. And the inequality flips, so that's less than or equals to minus xc on the other side. And now we add the same quantity on both sides, in which case we're going to be using mu c. And so you'll see that these two parts are going to be exactly equal to each other, and we'll be left with the inequality of this side less than or equals to this side. And before we go on with that, I'll leave the other part up in the corner of the screen. Before we go on with that, I'll just quickly write that down, because what we're going to be doing with this is taking the expectation of both sides of this inequality. So I'm not going to go into much detail on this, but basically you just need to multiply by the appropriate distribution and then integrate or sum, depending on whether you're dealing with discrete or continuous random variables, of course, and you'll have your expectation. There shouldn't be any problems with that. And so this is a step that we're allowed to do. Now what we said before, b is the truly best option, that's just a constant. Mu b is also a constant. And so we will be left with the constant mu b. And because of the linearity of expectation, of course, this expectation operator can be distributed over this linear combination. And then we're left with the expected value of the estimated value of the truly best option, which again is quite a mouthful. But what this comes down to is again mu b. This is just the estimated value for option B, which is mu b. And so this side evaluates to 0. And now we're almost done. We just need to rewrite this right side of the inequality a little bit, because we are then left with the expected value of mu c, which I'll just scroll quickly back up again, is the parameter that I said we would be proving the bias property for. And we were also left with, scroll back here, the expected value of xc, where c is the chosen option. So the expected value of xc is simply the expected value of the minimum over all estimated values, which is our estimator. And so just simply rewriting this, then we're already done. So this is greater than or equal to the expected value of our estimator. And this is the optimizer's curse proven. We can make this a little bit more interesting still, because this inequality can become a strict inequality. Now the way to see how this can become a strict inequality is to go back to the original inequalities that we started out with. Namely, this mu b is a constant, and this mu c is the expected value of the, or the true value of the option that we end up choosing. Now if it's at all possible that the chosen option is not equal in value to the truly best option, then this becomes in some cases a strict inequality. And then if we end up taking the expectation of this, then overall this inequality becomes a strict inequality. So now the condition for having this turn into a strong or a strict inequality, I should say, is if the probability of truly best option, so the true best value, being strictly less than the true value of the chosen option is greater than 0. Which basically says if it is at all possible to choose an option which has a true value that is worse than the best value that we can get, then this becomes a strict inequality. Alright, now I did just notice that I made a tiny mistake here. This should actually be, let me just erase this, this should actually be an I instead of C, since we're minimizing over all the xi, of course. But yeah, that just about wraps up this proof. Now of course this also holds in case of maximizing instead of minimizing, in which case the inequalities that we started out with are simply flipped the other way around. And so everything flips around, and yeah, you basically have a bias in the other direction. Instead of underestimating, you're all of a sudden, or you're then overestimating. Alright, so wrapping all of this up, today we've talked about the optimizer curve, which introduces a significant bias in lots of different situations. I haven't talked about all of these yet, but basically this estimator, this way of choosing the best possible sample out of a number of them, has the tendency to create a bias in all kinds of estimators, whether you're interested in estimating the value of a specific option, or the minimum value over all of the options, or estimating the true value of the chosen option. You will introduce a bias whichever parameter you're trying to estimate. And so what I think is the main takeaway from all of this is that you need to be careful when three things come together: optimization, picking the best option out of a number of different options; uncertainty, which comes in the form of probability distributions; and finally using value estimates to base further decisions on.